All right, so we just saw one example of a lever, so let's actually take a minute to talk about classes of levers. So classes of levers. Now there are going to be three types: first, second, and third class levers. And I'm not going to quiz you guys or test you guys over what's a first class lever, what's a second class lever. But understanding these setups and in principle, just how each of them work, will help you know what to expect when working problems. So let's talk about first class levers. First class levers has the pivot or fulcrum between what is called the effort and the resistance. Now, effort, just like the name kind of suggests, is the force that you put in. You are pushing for the effort. That is your effort. The resistance is what you're fighting against. So in our previous example, the effort was me lifting on the edge of the plank. The resistance was the weight of the object on the plank. So what does this look like? Our fulcrum needs to be between them. We would have an object. There's our resistance. There would be the force from the resistance. And we would need to be pushing down on this side. There's our effort. And I will try to use bold arrows for the effort in all of these, and then boxes to indicate the resistance. So you can sort of imagine trying to lift this box by putting in that effort. And if you can see, the effort and resistance have the same direction. If that fulcrum is between the effort and the resistance, well, pointing down on this side causes clockwise, pointing down on that side causes counterclockwise, and they can then balance. So in this situation, they have the same direction. It is down. We're typically going to have things pushing downwards, of course, just because of the direction of gravity. So they have the same linear direction of down, but opposite rotary directions. As I pointed out, one causes counterclockwise motion, the other causes clockwise motion. So this is how a first-class lever is designed, and this would be something like a crowbar would be an example of a first-class lever. And you want to make sure the length between the fulcrum and the resistance is short. The length between your effort and the fulcrum is long. That makes your work easier. When you're using a crowbar, you put that fulcrum very near to the resistance, like if you're prying open a box. Next, we have second-class levers. Second-class levers have the resistance between the fulcrum and the effort. The resistance is between the fulcrum and the effort, and this is like the example I just worked out of lifting the box with the plank. There is our fulcrum, there is our box with its force downwards, and then we can apply an effort to the opposite end to cause the box to move upwards. So the resistance is between the fulcrum and the effort. That's a second class lever, and as we just saw, this makes lifting easier. It makes lifting easier. You can think of it as multiplying your force by the length ratio. So we saw an example where we had 4 meters of length compared to 1 meter of length, and we got 4 times the torque for the same amount of force. Your torque is the force multiplied by the length. You get more torque by having more length. And lastly, we have third-class levers. Third-class levers have the effort between the resistance and the fulcrum. So what would that look like? Similar, but we have swapped the roles of the effort and the resistance. This would be like putting your box over here at the end, and then you having to push upwards in between the fulcrum and the resistance. And just like we made things easier in second-class levers, this sort of makes things harder. The effort force is larger. However, there are some advantages to this. Whenever you swing a rigid object, this goes back to rotary motion, the outside edge of that rigid object moves faster than the inside edge. Remember thinking about the record player spinning round and round? The outside of the record player moves faster. So there are situations where you might want to put your resistance at the end. You can maybe see if we were to launch that, it kind of looks like a catapult. Or you could imagine this being an arm. This could be your shoulder holding a baseball in your hand. Your muscles provide that effort and then cause your arm to swing up and throw that ball. You can get more speed out of something when it's at the end. It increases the speed of the resistance object. So think about throwing a ball or launching something with a catapult or a trebuchet. But this is very common. This is how our body works. All of our muscles attach on the near side, and then we have to push or lift things on the far side of our levers, our arms. So we'll work a lot of body mechanics problems like this, bicep curls, shoulder lifts, and so on. And this is teaches us why we should lift with our legs and not our back. You want to keep that resistance as close as possible so that your effort force is minimal. You don't strain your back whenever you lift things. But anyway, this is a brief overview of the classes of levers. We'll stop this video there and then talk a little bit more about static equilibrium and center of mass in our next video.